Okay, now we're back to our schematic. We're going to add some bypass capacitors, and I'll show you what we do and why we do it when we're talking about real-world applications. So if we go to our libraries, switch the libraries to devices, we'll come down here and we'll look for a capacitor. There's capacitor. So let's tell it place cap. There's the capacitor. I'll rotate it. And now I'm going to hit my tab key to change the properties before I place it, because I'm going to place 4 of these capacitors. So I don't want to see that. I want this to be 100 nanofarads, 0.1 microfarads, right? I don't need to see this comment. And I'll change this footprint to make it smaller. Let's see, I'm going to tell it add, footprint, browse, miscellaneous devices. Let's see. There we go. That's a small footprint. The radial 0.1, it's a 0.1 inch spacing. That's common for our 0.1 microfarads that we use here in this department. I'm going to tell it OK. And let's see, I'll place one here and one here. And then what might not be so apparent is I'm going to place one here and here. So I have 4 new caps there. Let's put our grounds on this one. And I'm going to move my power connectors and wire these in. I'll come across and wire these in very quickly. So you see I've added the 4 caps. I'll change my view so I can see everything. And now let's do our tools, annotate schematics quietly, update those parts. You see I'm moving my designators, and also that it's easy to read my part numbers. I'll tell it save, but I'm not done adding parts yet. I'm going to add 2 more capacitors, and then we're going to explain why. So I'll add a polarized capacitor. Place the polarized capacitor. I'll hit tab. Don't need to see this. This is going to be 100 microfarads. There, we can make it 47 microfarads. That'll be good enough for what we're doing here. Now, footprint. I'm going to tell it add the footprint. I'm going to make it a little bit smaller. So I'm going to edit it. Let's see. You know what we might do for this one is see if we can find a different footprint. Maybe we'll make these surface mount, just so we have some more variety on our board. We'll make it also a C1210. Tell it OK. OK. So now I have 2 surface mount polarized capacitors. Place one here and one here. I'll wire these in. I'll do tools, annotate schematics quietly, 2 more changes, save my changes. All right, now let's talk about what I did and why I did it. You'll see that I put 2 capacitors in parallel here, and actually a little bit farther down the board, I have 3 capacitors in parallel, all the same net, 12 volts DC. So these 3 caps are in parallel. And we know from our theory that when you put caps in parallel, they add. So it might not make a lot of sense at first to look at it. 47 microfarads plus 0.1 plus 0.1 is 47.2. Not a lot of gain. Doesn't seem to make a lot of sense. Why would I want to do that? Well, let's explain how these caps work. This polarized capacitor is the common ones we use here are made out of aluminum. They have two thin aluminum strips and a dielectric in between them. And these long, thin strips, they put the dielectric in between them and they roll it up so it makes a nice little round can that you see. And it gets a lot of capacitance because it's a lot of surface area. Now the downside is that capacitor has some internal resistance. They call that ESR, equivalent series resistance. And that ESR makes that capacitor a little bit slower to react. So to use an analogy, let's say that was a 5-gallon bucket of water. I can fill it and hold 5 gallons, but maybe the hole in the little socket that I hook it to put water in and out is small, so I can't fill it real fast and I can't empty it real fast. Now this little cap, the 100 nanofarads, it's made out of ceramic. They take a little ceramic disc, they plate some metal on both sides to make the two plates. It doesn't have a lot of capacitance. It's only 0.1 microfarads, but it has a very low ESR, very low equivalent series resistance. Because the resistance is low, I can put charge in and out of that cap much faster. So to put these two caps in parallel, I now gain the properties of both those caps. I can store a lot of charge, and for a short duration I can change or move my charge quickly because of the 0.1 microfarad. That's why I have these two in parallel. Why do I have this one over here by this active chip? Well, the reason I did that is, and I'll just draw on here and we'll remove it when we're done. Let's say on our printed circuit board that the trace moves like this all over the board, goes to all these different places. It becomes a long, thin trace. Right? It looks crazy, but eventually the trace comes here. So now I have this long, thin copper trace on my printed circuit board. Well, what happens, right? Every conductor has resistance. Even copper, which is a good conductor, it has resistance. So as I move my charge all through that long, thin trace, I have resistance. That's going to slow down my movement of charge. Also, that long, thin trace has inductance. So at fast current spikes, that inductance is going to slow down my current. So what I do to protect against that is for every active component, that would be your microprocessors, your op amps, any part you put in, your DAC that's an active component, I put a 0.1 microfarad from its power pin to ground. And you'll see later when we lay the board out, I'm going to make this little cap be very close to this IC. And these two caps are going to be very close to their power source. One more thing to consider is this power source, I don't know where it's coming from. I have no control over that, right? So this could be 100 feet of wire. What happens 100 feet of wire? I get inductance, I get resistance. So I need this big cap and a small cap to clean my power up here. I need this small cap to clean my power up here. That's why I do that. Now I'm going to remove that. We don't need that great big trace. But you'll see now I have my op amp circuit, my input, my output, right? I have my feedback resistor here, my input impedance resistor, gain of -10. I have my bypass caps. I have a connector here to get power on the board. I basically have everything I need here at this point to move my parts over to the circuit board. When we move the parts to the circuit board, it's going to open a whole new can of worms. We're going to look and see what do we have to do on the circuit board to make it work. Oh, one more thing to mention here. You'll see that this cap is upside down from this cap. And why did I put it upside down? Well, these caps are polarized. If I reverse bias that capacitor, it kind of looks like a diode in a way. If I polarize it correctly, no current flows through it, it stores a charge. If I polarize it the opposite direction, it will just shunt current to ground, get real hot, it'll swell up. The top of the cap will start to swell up, and the aluminum on the outside will crack, and it'll vent gas out, and the whole story's over. You can throw it away. So you'll see what I did. It looks like it's upside down, but what really happens, this is minus 12 volts. So this side of the cap is more positive than this side of the cap, and that's why I put it in that direction. These little 0.1 microfarads, they're not polarized. It won't matter which way they go in. They're happy the way they are. So we'll end this video here. In the next video, we're going to move our parts onto the printed circuit board and see what we have to do there. Thanks.